And good morning, class. And learning objective today is to measure the force on a tin of beans. Newton's second law of motion, page 144, chapter 10.1 of the physics textbook. Now, this is an extremely important practical for you to try at home. And just because you're at home doesn't mean to say you can't do practical science. After all, Newton didn't work this stuff out by staring at books. He actually watched apples falling off trees. Well, we're not using apples, we're going to use tins of beans, and the reason for a tin of beans is because it's got a clearly defined mass on it, and I want to know what that mass is for later. And then ask your parents before you get tins of beans out of their hidden store cupboards. They're likely to get a little bit sort of jumpy that you're playing around with their beans. Now, we're going to do this experiment. We're going to try, and just like as we have done in class, I've measured out a board. You can use any old piece of scrap wood at home, and I've measured out a starting point 10 centimetres into the board just to give me space, and I'm going to stop it at 50, and I'm going to use just a standard digital stop clock to do this. You can obviously use your phones. So let's stop this thing and reset, and simply place the beans on. They usually go down pretty well. You place it on the starting point, start, let it go down, stop, and you do that repeatedly. Get several readings. I mean, you're at home, so you could afford to take, say, 10 readings. It's all good science, and you can see there how easy it is to do that. And so give me a moment just to move all this out the way, and this is the sort of results you will then get. So to measure the force on a tin of beans, Newton's second law of motion, you have to know this off by heart. Force equals mass times acceleration. F equals ma. Force is newtons, mass is kilograms, and acceleration meters per second, meters per second squared. And you need to know these units now, please. And so here's a set of results I did earlier using exactly that equipment, and my distance is 0.4 of a meter. Now remember, it was 40 centimeters, and 40 centimeters I have to bounce a decimal point two places to get 0.4 of a metre. So there are 100 centimetres in a metre. Now the exam board will expect you to do this quite easily all the time. So that's why it's 0.4 of a metre. Many students make mistakes in the exams where they change the units and the students don't spot it. Always keep in metres. So times seconds, 1.91 second. Now my velocity from the previous lessons is distance divided by time, measured metres per second, ms minus 1. It's gone a bit blurred there on the board. 0.21 if I divide these two things out. And to get acceleration, a is going to be the difference in the velocities, v minus u over t. U was 0. So therefore my acceleration is going to be v over t. As I divide by time again, I get 0.11 meters per second. Certainly good enough for what we're doing today. To come down to my second table here, I'm now using my Newton's second law of motion. F equals ma. The acceleration has come from here. The mass is off the tin of beans. That's why I chose them, because they show quite easily what the mass is. So let's have that. You don't have to use beans. Earlier I tried a Satsuma, but I couldn't work out its mass. Something where you know the mass, and the beans roll so well. And again, the mass is 0.2. It's down on the tin as 200. And I've got to bounce a decimal point. This is the one I've got to bounce it 3 places, because there's 1,000 grams in a kilogram. And I've got to have this in kilograms. You mustn't forget to do these conversions all the way through your physics. And then F is mass times acceleration. I can multiply the two together, 0.022 of a newton. My last point then with this, you saw at the top, F equals ma. So newtons equals, the mass is kilograms times acceleration, meters per second, ms minus 2. And why is that important? Well, the exam board are very fond of giving you an exam question that gives you 4 choices. And it says, what is the alternative measurement for a newton? And they do exactly what I'm doing here, and they put in 3 distractors. And you can, when you're in the exam and you're tired, it's very easy to get that wrong. Your entire brain freezes up. And the way to deal with it is to say, I don't need to remember that ever. All I need to remember is F equals ma. I know that Newton equals the mass, kilograms, times acceleration, meters per second per second. Now that's an extremely important chapter in the book. If you can't access Caboodle, I don't blame you. Yeah, it's not an issue. If you look up Newton's second law on BBC Bitesize, they deal with it fantastically, and just go through the chapter there instead. But try the experiment at home. Now, I'm going to expect you to have written this up in your exercise books and clearly indicated where it is. I'm going to look for the quality of the write-up. I'm going to look for a method. I'm going to look for the accuracy. How have you managed to keep it accurate? What did you do to make sure that it is repeatable or reproducible? So I want to see this information, please. And your conclusion, of course, is for a tin of beans in my case. What was the force on it? Of course, the slope was at that angle. There's a lot more you could do with this, but that's the point I want everybody to show me when we almost certainly will reconvene in the summer. The thing is, your course can't stop. We can't go over all the missing work in quite the way you might think. There just isn't time. Now, the exam boards may make alterations because of what's been happening, but we can't gamble on that. So please try this at home. It's good fun. It'll take you about an hour to do a good experiment and about another half hour to write it up, and it will get you out your seats. Right, thank you very, very much. Keep safe.